Are you able to listen to me? Devendruva? Devendruva? Siddharth? Are you able to listen to me? Siddharth? Shruti?
Yes, sir.
Okay, fine. So we'll start our discussion, and first I will share the. Okay, are you able to see the slides? Please respond, one or two people.
So we can see the slide. So can you record the session?
Okay, that I will do it once we first start before starting. Okay, start recording. I put just now start recording. Okay, fine. So. Okay, so in previous classes, we started discussing about, first we discussed what are the crystal structures, what is importance of crystal in understanding of matter, depending on how can we describe a crystal in terms of symmetry considerations. We divided the matter into three ways: crystal, then polycrystalline, crystalline and polycrystalline and amorphous disordered systems. After that we discussed possibility of existence of 14 Vivace lattices. We tried to understand basically crystal structures at the beginning, started with theoretical understanding by utilizing symmetry groups to the solids. By developing the theoretical framework, we came to know possibility of 14 Vivace lattices in cubic crystals, hexagonal crystals, orthorhombic crystals, like that. Then we discussed the structure of diamond and some other materials, single basis materials, metals. After that we discussed how to label the planes of, groups of planes of, or direction of planes in this crystal by HKL parameter, means. Then we discussed about how to calculate Miller indices, and then we discussed about how to calculate the angle between two planes or two directions. After that we discussed what is called the closed pack systems, FCC, and hexagonal HCP structures. And then we found closed pack structures have near about 75% occupancy by atoms, whereas loosely packed cubic crystals have 50%. Then we discussed the importance of nanomaterials or nanoparticles in terms of surface to volume ratio for catalysis properties. Then afterwards, in previous class, we discussed actually what is nano, and mostly we discussed what are the low dimensional systems. We discussed in previous class 2-dimensional, 1-dimensional, 0-dimensional materials which will exhibit quantum properties, quantum confinement of the energy levels in 1, 2, and 3 dimensions. I hope you are getting my point. all the charge carriers are confined in all 3 dimensions. It is called 0-dimensional system. When charge carrier is confined in 2 dimensions, means then it is called 1-dimensional system. Then if charge carriers are confined in 1 dimension, then it is called 2-dimensional system. So we discussed all these things, and then we have shown some examples of what is called the nanoparticles, quantum dots, and we discussed very briefly about an experimental technique called transmission electron microscopy. So those things we discussed. So now we are discussing one more important topic called length scales. Length scales. Basically, as we started discussing in the previous class about the importance of this topic, basically we must know what is the what size of what is the dimension of the nanoparticle, which can be called as nanoparticle. So what it means by that, basically, as we discussed in the previous class, what is nanoscience and technology? Basically, from solid to atom, solid to group of atoms. Solid means what? In one unit number of atoms will be there, which is called 10 power 26.020 10 power 20, huge number. In 1 mole of a material, 10 power 23 atoms will be there. Very huge number. Because of that huge atoms coming closer and closer forms a solid, then each atom's energy levels will superpose with other atoms' energy levels and form corresponding energy bands, as we know very well. You know these things, valence band and conduction band, because we are more concerned with electrons which are very close to the Fermi level, whether more than energy more than Fermi level or lower than Fermi level. So lower than Fermi level is called valence band. More than Fermi level energy levels band is called conduction band. So you people are very much aware, I hope, that valence and conduction band. So then below valence band, there are bands called core bands. So basically, that means starting from nucleus, K, L, M, like that thing. Means K band, L band, like that. So that means basically what we are talking in previous class is that when in nanoscience or technology, basically we will concern with a material which is not macroscopic, but not even not microscopic, but nanoscopic. So number of atoms in that solid is very number of solid atoms is very small in comparison to micro or macro materials. So because of that, what happens? The width of the band will become very less in comparison to macroscopic or microscopic particles. I hope you are getting my point. Okay, in previous class we discussed this thing. That means as we are coming from macro, micro to nano, number of atoms in the solid which we are considering will be very less. Then what happens that then what we can think about it? Then we can think that the width of the energy band, either it's a valence band or conduction band, will be very small in comparison to macroscopic valence band, material valence band, or conduction band. So one of the important direct effect of decreasing the size of the material is the valence and conduction band width will be decreasing. So it is directly towards the ideally speaking in atoms. Atom like means discrete energy levels. So that means because of the discreteness of energy levels, the materials which are going towards nano will have what is called quantum confinement. So they are called low dimensional systems. So that means basically what is important thing for us, at what length scale, at what nanomaterial size, quantum mechanical properties set in. Are you getting my point? Quantum mechanical properties set in for a particular property of the material. So that dimension is called length scale of that particular material for that particular property. Once more I will talk. What is important thing for us is now nanomaterials should have very small bandwidths corresponding to nearly to the what is called group of atoms. One single atom will have what discrete energy levels. Group of atom means energy bands will have still some width, but it's very much less in comparison to the macroscopic or microscopic materials. So since the bandwidth decreases, what's called of the orders. I hope you understand what you mean by order. Order means, let us say 10 power 3, 10 power 2, 10 power. These are orders of difference. Third order 10 power 3, second order 10 power 2, first order 10. So like when three orders less means 10 power 3 to 10 power 0, like that. That means width of the conduction band or valence band decreases drastically when we are coming from macro to micro to nano. So because of the decrease of bandwidth, then what will happen? Some type of discreteness will come into play in the energy levels or group of energy levels of the nanomaterial. So when slowly coming into discreteness means quantum mechanical property will come into play. So at what dimensions of the particle the material will exhibit or start exhibiting, not necessarily exhibiting, but start exhibiting what's called quantum property, then it is called what is called nanomaterial or length scale of nanomaterial. It may not be totally quantum, but it is now closer to quantum material or quantum particle. Or get my point? Still, the width of the conduction band or valence band will be finite. It is somewhat higher than the single atom band width of the discrete energy level. Okay, so it is not directly, we are not directly going into what is called quantum level, but we are approaching quantum level. In previous class, I told one more thing also. Macro, micro, nano. In between micro, nano, there is something else called meso. Meso. It is neither what's called classical mechanics or totally quantum mechanics. It is in between. So we can think nanomaterial or nanoparticles having mesoscopic what's called sizes. It is neither fully follow classical mechanics or fully follow quantum mechanics, but it start up following the quantum mechanics, more in towards the quantum mechanical description we can give. So that type of what's called that type of sizes or dimensions of the particles is called length scales. In below that length scales, now fully partial confinement of a charge carriers or fully confinement of the charge carriers will happen. And one important thing, as I discussed at that time also, for a part, we have to define length scale of a particle, length scale of a material for a particular property and for a particular what's called material. So for example, if we take metal, as we discussed in previous class, metal and conductivity, electrical conductivity. So metal, if you take metal and electrical conductivity, then in metals, what is the charge carriers? Electrons are charge carriers. So electrons, what is conductivity, electrical conductivity? Electrons move from one place to another place in the given what is called sample. So that means electrons are moving in the electron C in metals, SESC. Then because that one particular electron will can encounter many number of electrons, so because of that it suffers multiple collisions. Then what will happen at each collision, direction of the movement of the electron will change. So because of that, what will happen? The electron moves zigzag way. So as I told in the last class also, please imagine that since you are in electronics department, you are in AB5. When you are physically present in the institute, so you imagine. I think you should recall how you are going outside of AB5 through that bridge, what's called exit. Then so many people will come such that they would like to take refreshments while class break, in between class breaks. Then what will happen? So many people are coming. If a particular person to coming outside, he cannot travel what's called straight line, but he has to just go zigzag point so that he comes out of the AB5. So similarly, electron, while it is passing through the material under the electric field condition, it encounters many number of what's called many number of collisions, and thereby it changes its path. So the distance traveled by the charge carrier, the distance traveled by the charge carriers between two successive collisions is called. Last time I told what is that thing? That is mean free path. So mean free path is a relevant length scale for the how much is the mean free path of a electron for a particular material.
Sir, you have been muted.
Okay, fine. Thank you very much. Okay, so please don't do that type of things because I may not be able to observe if somebody mutes me. So please don't be like that. Please try to just concentrate on the discussion rather than putting that type of things. Okay, I request please don't do any mischief like that thing. Because I may not, because I have to minimize to make you see the what's called blue slides. Okay, please don't do that. Okay, now that means we have to. So now at this stage, so length scale, relevant length scale for a metal for conductivity property is what is that thing just now I told? Mean free path. Mean free path. Similarly, today we are discussing about length scales of semiconductors for optical property. For optical property. Okay, so what is meant by, as all of you may be aware, you are aware that what will happen if a semiconductor absorbs what is called optical energy. What mean by optical energy? If you take a semiconductor, since you know silicon very much, let you take silicon only, for example. Now, once you take silicon, then what will happen if you put some light on the some light energy on the semiconductor silicon, then what will happen? The energy given by the light radiation is absorbed by the material, and one electron from valence band excites into the conduction band. So then what will happen? It is basically electron in the conduction band, hole in the valence band. So now because of this type of excitation, so what is called one electron hole pair, electron conduction band, hole in the valence band. So the electron hole pair will form. So now for any semiconductor, not necessarily silicon, for any semiconductor, if you irradiate that semiconductor with appropriate light, why we call appropriate? Because energy of the radiation, optical radiation, should be at least equal to higher than the band gap of that semiconductor. Then electron can transform from valence to conduction band. Otherwise, it is not, as you know. So that because the absorption of light energy by the semiconductor, then electron hole pair will happen. So now you know the conductivity property or any other property, optical property of the material semiconductor depends on how electron hole pair behaves under the conditions. So now that means that is an important thing. There are two, that means in semiconductor for optical property or for any other property, there are two types of what is called charge carriers, electrons and holes. For metals, only electrons. For semiconductors, electrons and holes. So now these electron and holes, how these electrons and holes can be confined. What is the size of the nanoparticle or size of the particle wherein both electron and holes are confined? Are getting my point? That length or size is called length scale of the semiconductor, of the given semiconductor for optical property of the material. So this is what we are now going to discuss. So first we have to discuss, so how can we discuss then? So now how electron and hole, in after formation of electron and hole, how these two are related to each other. As you know, one electron, see electrons in the conduction band of semiconductor and is not equal to electron of the conduction band of the metal. Why? In metal, electrons are free electrons. Electrons are free electrons. That's what it's called, free electron C, SEAC. Because electrons can travel freely. What do you mean by freely? They don't have any Coulomb interaction, or any Coulomb interaction that may be there can be neglected. That's why it's called free. FRE free. So electrons in the conduction band of metals can transport from one point to another point in the sample without any interactions. Only interaction is Coulomb interaction, electron-electron repulsive interaction. So because of that, it loses some energy and its direction. But in semiconductors, there is not in conduction band there are electrons. Number of electrons are high, so electron-electron collision is possible. But in addition to that, there is a Coulomb interaction, attractive Coulomb interaction between electron in conduction band and hole in the valence band. So because of that, what will happen? This interaction dominates. So and decides how electron hole pair, which is also called exciton, how it will behave. Whether it is confined in one dimension, confined totally in given dimensions, it will determine. So now we have to discuss how can we know what are the dynamics of electron hole pairs in the well in the
So we can't hear you.
is it fine? Are you able to listen to me?
Yes, so now we can hear you.
Oh, sometime just 2 minutes, there is some error came. Now is it fine?
Yes, sir.
So now that means we have to understand. So what is the length, what is the size of the particle in which the electron hole pair together or individually electron and hole will get confined, will have some quantum, will exhibit some quantum properties. Okay, now that is our requirement. Once more I will talk. Now we should understand what is the size of the nanoparticle or size of the particle of semiconductor wherein the exciton or electron hole pair together will have some exhibit quantum property or confinement property, or electron and hole separately will exhibit confinement property. So that is what we would like to know. Okay, I hope you get my point. Now we want to understand, we want to travel towards the what I just now told. I think all of you are aware about matter waves. What is matter waves? As you also know, the electromagnetic wave. Electromagnetic wave. So electromagnetic what's called particle. I hope understand the electron. You can have the photon can behave more as a particle as well as wave. So it's called wave particle duality. That is first important what's called understanding. And at the beginning of 19th century or 1900s, people found. So that means electron, and similarly, the electron has both has property of both particle as well as wave property. So because of that, people should know how to describe the electron in different conditions, where electron behaves wave nature or exhibit particle nature. So it depends on how we look at it. In the sense, what type of experiment we try to do, what type of experiment we try to design to understand the properties of electron. Accordingly, we will see the electron. So what is meant by that? I think you may be aware. I think you may be aware that important property of wave. Three important properties of waves. What are that thing? Interference, diffraction, and polarization. So now that means basically interference will directly tell that photon is a what is called wave. Polarization also what is called wave. Diffraction also wave. But I think you may be aware there is a photoelectric effect which will tell us photon is a what is called particle and electron is a particle. So like that. So that means basically subatomic particles will both exhibit both electron and wave property. So, but only according to what type of experiment we do, accordingly we will see the particle behaves in that way or wave behaves in that way. So De Broglie in his PhD thesis proposed this dual concept of wave particle duality. So that means he gave one equation which will have both wave property, which will connect wave property and particle property. What is wave property? De Broglie's equation is lambda is equal to h by p. What is lambda? Lambda is wavelength. H is a constant which is called Planck's constant. P is momentum of the particle. See, as you, I think you are aware, in classical mechanics, P equal to m and a. M means mass, a means acceleration, or mv, momentum of the particle. So that means basically momentum of the particle, okay, the word itself, the momentum itself will tell us it is a particle. We are talking about momentum means momentum of the particle. Momentum of wave will not be there. Lambda means wavelength of the particle. Energy of the, sorry, lambda wavelength of the wave. Energy of the wave. Okay, momentum of the particle. So that means basically de Broglie's equation will connect wave-like nature lambda and particle-like nature momentum of a what's called subatomic particle. So that's why he clubbed these two seemingly not in contradiction with each other. A particle cannot be wave. A particle cannot be wave. A particle cannot be a particle cannot be wave, or wave cannot be particle. But both will exist according to depending on how we see. So I will try to 1 or 2 minutes. I will try to explain. I hope you people know this, but I want to put it in more better manner such that you will appreciate the discussion there. See, a current means you see electrical current. So electrical current is passing through a wire. The moment we cut at one place of the wire, then what will happen? Then, as you know very well, naturally wave cannot pass through beyond that point. Then what will happen? It will reflect there and go back inside the what's called wire. So that means basically beyond the point of the disruption, wave will not be present. So that means basically a wave cannot be both have particle property. Once we abstract a wave, it is no more a wave. Okay, like that. I hope you get my point. So now that means Planck's constant is 6.62 in 10 power minus 34 joules second. Okay, please remember this. I would like to say one thing to you. So some fundamental constants are there. Now at this stage, H Planck's constant in examinations, whenever we use some problems, I may not give physical constants, value of physical constants. I expect all of you to remember this. Okay, so please, you should remember some of the important physical constants. Okay, I advise you must. So H lambda is equal to H by P. So this has both wave property and particle property. Now we have to talk about de Broglie wavelength and exciton Bohr radius. What is meant by that thing? What is meant by that? Basically, we have to take an atom, hydrogen atom. Why we take a hydrogen atom? Basically, hydrogen 1 electron, and in the outermost energy 1s orbital 1 electron, and then 1 positive charge at the nucleus. So that means what will happen if you take hole? As you know, hole in the semiconductor is has a positive nature, and electron is a negative nature. So in semiconductor, exciton means electron hole pair and negative positive charges separated by distance. That is called exciton, which will happen because of the absorption of light energy. So now we have to understand, our goal is to understand exciton in the given semiconductor. But semiconductor has so many other electrons and all those things in the atoms and other things. So simplest possible model we have to take. What is simplest possible model? Basically, simplest possible model is for exciton is hydrogen atom. So hydrogen atom or hydrogen atom. Now you see hydrogen atom has what is called. So one hole means positive charge means nucleus, 1 electron in the what is called in the outermost energy electron, 1s electron. Now we are consider a hydrogen atom in its ground state. Why we talk ground state? I think you may be aware in your 12th class or first year BTech, you might have studied what is called optical spectroscopy. Even though it looks very simple, with one electron in the hydrogen atom it has lot more what's called spectroscopic properties, which told us there are so many energy levels other than 1s. I think you are aware of that, but we don't go into that thing. So that's why we call it ground state. If in excited state, then electron need not be in 1s first orbital, 1s orbital. It can be 2s orbital or 2p orbital or higher energy orbitals it can be in the excited state. But we don't want that type of situation. We want simple ground state hydrogen atom. So that means electron is revolving around the nucleus in 1s orbital. You know 1s orbital means S means spherical. So it is spherical orbital. Okay, I hope you understand this thing. So now the important thing is that electron is moving in a spherical motion. Okay, in a spherical path, Okay, in a spherical path, having center of the sphere or center of the circular sphere is nucleus, positive charge. So that means there is a electrostatic interaction between electron in the orbit, hole or positive charge in the nucleus. So now we can say there is a very good, this model is having a very good what's called spherical motion. So in spherical motion, if an object is in spherical motion, then it will be acting upon by two forces. What are the forces? Centrifugal force towards the center, centripetal force away from the center. So there is attractive interaction between the electron in the orbital and positive charge in the nucleus. So it's called Coulomb interaction. So now that means since electron in the 1s orbital is continuously traveling around the nucleus in the spherical part, and since hydrogen atom is existing in nature, so the forces that are there on the electron, which is centripetal force or centrifugal force or Coulomb force, all forces are balancing with each other. So we can write an equation. What I think you are aware about centripetal force or centrifugal force. What is that thing? Okay, mv squared by r. I hope you remember this. M is mass of electron, v is velocity of the electron, r is the radius of the orbit. Then this is centrifugal or centripetal force. Then what is Coulomb interaction? There is a Q here, there is a Q here. Q means charge of the electron or hole, charge of electron or the nucleus. So M1 M2 by R squared means M1 means Q, M2 Q squared. In 4 pi epsilon 0 is a constant. So Q squared by 4 pi epsilon 0 R squared. Okay, so it's very simple. I think you may be aware of all these things, but please don't mind if I'm talking more ABC, I mean more fundamental. Please don't mind and be patient with me because you may be aware, some of you are aware of the things, but I want to explain so that every one of you will have a good understanding. There should not be any confusion later. Okay, so now that means basically, so there is a now in equilibrium condition, the centrifugal force equal to Coulomb interaction. So mv square by r equal to q square by 4 pi epsilon 0 r square. Now radius of what is epsilon 0? Permittivity of the medium. Which medium? Where where the hydrogen atom is situated. Let us think the hydrogen atom is an isolated hydrogen atom in vacuum or in air. Okay, so that means permittivity of the medium, epsilon 0. The permittivity, I hope you understand this. So since the electron orbit is 1s orbital, which is spherical in shape, an integer number of wavelengths should be fit in circumference. So how many wavelengths will be there? Integer wavelengths of the circumference. So wavelengths means 2 pi r. 2 pi r is the circumference of the 1s orbital equal to the lambda is, what is lambda? Wavelength. Okay, so n lambda, n is integer number. What is lambda here? Lambda wavelength of electron. Wavelength of electron. So that means lambda. So now we can write, we have with putting de Broglie's equation here, L is equal to lambda is equal to h by p, h by mv. So 2 pi r by n. Okay, you understand what I'm telling? Lambda is equal to h by p, which is de Broglie equation. H by p, p means momentum, h by mv. So in the with this equation, lambda equal to 2 pi r by n. So we have this equation. Lambda is equal to h by p is equal to h by mv is equal to 2 pi r by n. N is, what is n? It's integer number. Since we are taking one single first orbital, which is called n is equal to 1. For second orbital, n is equal to 2. For third orbital, n is equal to 3. But here we don't give 1, 2, 3 number, but we will say n, which is a generic number. It can be n 1, 2, 3, 4, depending on what type of orbital, which orbital, first orbital, second orbital, third orbital we are discussing. So solving for V, I hope you can do this very well by yourself. So V means velocity, okay, is equal to nh by 2 pi mr, n h cross by mr. H cross means basically h cross is what? H by 2 pi, which is called reduced Planck's constant. Reduced Planck's constant. So n h cross by mr, r is radius of the orbital. So replacing it into the main equation, putting this equation, v is there, you put here, mv square, you put that v here. Okay, then we can get n square h square by mr equal to q square by 4 pi epsilon 0. Rearranging this equation, we get r equal to 4 pi epsilon 0 n square h cross square by mq square. Okay, all of you, I request all of you, just don't see the view graph, but put in your notebook and solve this equation, which is very easy. But I request all of you to put all these steps in your notebook such that you have written once, at least once in your notebook, such that you will not have any problem of understanding later when you see this thing. Okay, so Aryaman Banerjee. Aryaman Banerjee.
Yes, sir.
So I request you to have your notebook with you and write these equations.
Done, sir.
Okay. So I am requesting each and every person like this thing. Okay, Ayush. Ayush.
Yes, sir.
Please write all these things in your notebook.
Yes, sir.
Please do that things. Tarun, please do. Because it may look very easy while you are listening, but once you write in your notebook, it will be easier for you to understand things and remember things. Aditi? Aditi?
Yes, sir.
Please write in your notebook, madam. I will give you some time. I will give you some time for you to write these equations. Okay, I am putting the de Broglie wavelength and exciton Bohr radius. Please write the steps in your notebook. I will wait 1 or 2 minutes. Are you writing? Please respond. Some of you please respond. Are you writing in your notebook?
Yes, sir. Writing.
Please do, sir. Because I feel one thing. Just by listening, you may listen and forget. But if you write, one time of writing is 10 times reading. Okay, and further it will be there on your notebook, which you can refer at any time. Okay, how many people wrote? Please put your hands up. Please put your hands up. Who wrote it already? Okay, 3, 4 people. Fine. Okay, and thank you very much. Okay, now we start again. So please write whenever I'm talking this type of derivations understanding, please write in your notebook. Last time also I should have insisted, but I didn't insist. Now I am trying to say same thing. Okay, so now we have derived an equation for r. R is small r equal to what is radius of the orbital, first orbital, radius of the orbital, 4 pi epsilon 0 n square h cross square by mq square. Here, so 4 pi constant, as you know, epsilon 0 is constant since it is in a known medium or a vacuum or air. H is a constant, m is constant, m is what? Mass of electron, q is charge of electron. So that means r is a constant radius. So if we put n is equal to 1, then this gives what is called r equal to a0, small a0 equal to 4 pi epsilon 0 h cross by mq square, which is called Bohr radius. First orbital radius in hydrogen atom, first orbital radius is given by a0 equal to 4 pi epsilon h cross square by mq square. This is most important parameter for many things. For hydrogen atom, it is for hydrogen atom. It is for hydrogen atom, first orbital, 1s orbital. 1s orbital. As you may be aware, in first energy level, only one sublevel will be there, which is called S, spherical. In second orbital, S and P. In third orbital, sorry, in third main energy level, first energy level S, second energy level S and P, third energy level S, P and D, fourth energy level S, P, D, F. I hope all of you are aware of these things. You may be aware, you should be aware how electrons are arranged in their in energy levels around the nucleus. Okay, all these are fundamentals you must have studied already, and at least you should.
Say muted.
Hello? There is again, now it's fine. Is it okay now?
Yes, sir.
Yes, sir.
I don't know, sometimes some error is coming. Okay, fine. Okay, so now that means basically we have derived an equation for calculating or to determine the first radius of first orbital of hydrogen atom. which is a constant. So if the electron is a, so then if this hydrogen atom is put or electron is put in any other dielectric material which is having the dielectric constant to be epsilon. What is what is called dielectric? What is meant by dielectric constant? Relative permittivity. So epsilon should be replaced by epsilon 0. Epsilon is permittivity of the medium, and epsilon 0 is permittivity of what's called the vacuum. So we have to replace epsilon 0 with epsilon and epsilon 0, where epsilon is the dielectric constant of the material or dielectric material in which the electron is situated. Okay. So what I'm trying to say here in this case is that now up till now this point we are considering the hydrogen atom. As you know, as we just now discussed, what is the hydrogen atom? It is there is interaction between electron and hole. Hole is positive charge, which is nucleus. Electron is in the first orbital. So we can take hydrogen atom as a ideal what is called exciton, electron and hole. Combination of electron and hole, which is called exciton. Now, if we talk about a real semiconductor, there also you can take one electron and one hole, which is excited from valence to conduction band. So then what will happen? But we can consider hydrogen atom concentration there also. But now the surrounding medium is semiconductor, which is having some dielectric constant value. I will talk about what is dielectric constant few minutes later or tomorrow. So that means basically we have to replace epsilon 0 with epsilon 0. Okay, so now that means A0 is 4 pi epsilon 0 epsilon 0 h cross square by mq square, where the hydrogen atom or electron hole pair is in the medium of having dielectric constant epsilon. Okay, so now if you take epsilon 0 is equal to 8.85, 10 power minus 12 farads per meter, h cross is equal to this much, me means mass of electron is this thing, q is this. So please all of you take these values and calculate A0. Please don't see here, but take your own calculation by utilizing what is called calculators, and then try to say calculate what is the A0 and like that thing. Okay, please don't see the view graph, but calculate by yourself. Please see the values here, but calculate A0 by yourself. Okay, I will wait for you and then do it by yourself. Don't see the view graph. And let me know you got similar answer or not. I'll wait. Epsilon is equal to epsilon 0 equal to 8.85 10 power minus 12 farad per meter. H cross is equal to h by 2 pi equal to 1.054 in 10 power minus 34 joule second. Me equal to electron mass equal to 9.11 into 10 power minus 31 kg. Q means charge of electron is equal to 1.602 into 10 power minus 19 coulombs. Now please calculate A0. Are you calculating? Please respond, one or two people. Ariman Banerjee, are you doing it?
Yes, sir. Doing.
Okay. All of you, please do that. Please, at least one of you should tell, two people should tell me what is your number. Rakesh Ravindra, are you doing it? Rakesh
Yes,
Ravindra?
sir. Yes, sir.
Okay. Did you get answer?
No, sir, I'm still calculating.
Okay, okay. This is you should get 5.28, 5.2 10 power minus 11 meters equal to 0.528 angstroms. 0.528 electrons, sorry, angstroms. Roughly 0.5 angstroms. It's already almost 3 to 4 minutes we waited. What, sir? How many people are doing it? Anyone can tell the answer? Aryaman Banerjee?
So I got 5.284 into 10 power minus 11.
5 point?
284 into 10 power minus 11.
We are closer to that, but still there is some small problem. As I understand, this is basically, you see, it is 5.28, 10 power minus 11 means 0.2 meters. So what is angstrom? 10 power minus 10. So that means if you do like that, it is basically 0.528 angstroms will come. Did you get same thing?
Yes, sir.
Aryaman?
Yes, sir.
Same, exactly same?
Yes, sir.
Fine, very good. Okay, tell any other people are got it? Ayush? Ayush? Rakesh? Rakesh? Aditi?
Yes, sir.
Who is that? Rakesh?
Yes, sir.
Did you get similar thing?
Yes, sir.
Okay, fine. So now what I would like to say is that basically it is important for you people to do this type of problems because it may look very easy because only substitutional problem, but it will give a very important insight into the material or understanding. That's the important thing to remember for doing this type of problems. Basically, A0 means what? As we discussed, the radius of the first orbital, 1s orbital in hydrogen. So that means basically what people do is that in calculating other atoms other than hydrogen atom, let us say I ask one question. Hydrogen afterwards helium is there. Do you feel helium atom also has having first orbital will be same? Do you feel like that? I ask one question to all of you. Hydrogen first orbital, 1s orbital is having 0.528 angstrom. So what can be the first orbital, 1s orbital radius for helium atom? It will be more or less. Can you think and talk? Hello? Any one of you? Since you calculated first orbital, 1s orbital radius of hydrogen atom to be 0.528 or zero point 0.5 angstroms, can you say 1s orbital of helium also will be same or different? Ayush? You people should
Yes, sir.
So do you feel that 1s orbital of helium atom will also have same dimension than in comparison to hydrogen?
No, sir.
Why?
Sir, it has an extra electron now.
Extra electron and
Yes,
extra proton,
yes,
both extra. So moreover, 1s atom, 1s or the, hello.
yes, sir.
So that's why more heavily it will be shrinking.
Yes, sir.
That's why it may at least we can say with first principles it may not be equal to, it can be lesser than 0.5 angstrom. Is it not? So we will see why I'm trying to say is that what I'm trying to say, by calculating 1s orbital radius of hydrogen, we can think of what can be the, at least with other higher quantum mechanical calculation or other things, interactions, vagera, we can at least think and what can be the 1s orbital of other atoms. It can be lesser, but how much lesser and other things will depend on the details. But it is important to know in a qualitative manner, it may be possible that 1s electron, 1s orbital radius can be smaller for any other atom, can be smaller than hydrogen atom 1s orbital. Okay, you got my point, I think. So now that means basically, so this is what important thing. In case of semiconductor, we have to consider exciton. What is exciton? Just now, as I sometime just I was discussing exciton. What is meant by exciton? Exciton is electron and hole. So in when we talk about a hydrogen atom, we considered the mass of electron and mass of positive particle, which is nucleus, are same. We thought like that. That's why we put only m. H is equal to 4 pi epsilon 0, 4 pi epsilon 0 epsilon h cross square by m2 square. M is mass of electron we put. We consider like that. But if we take real world situation, exciton in a semiconductor, so here electron and hole are both are there. We cannot put mass of electron is equal to mass of hole. So we can, it is possible that mass of electron is need not be mass of hole. So two different masses having two different charges, mean not positive or negative charges, will come into picture. So what we are see, I think you should understand one important thing, how we are approaching the problem. We are approaching the problem with simplistic consideration and slowly we are putting the what is called modifications in the equation or concept by real world understanding. This is how people develop understanding. Okay, so we cannot just try to start straight away talk about exciton without simplifying the situation. So we started with hydrogen atom to make the things simple. Then we took it when first we discussed hydrogen atom in vacuum, then hydrogen atom in some medium having dielectric constant epsilon. Then afterwards we are now discussing a actual semiconductor, wherein actual exciton will happen once optical energy is absorbed. So electron and hole pair is will happen. Electron in valence conduction band, hole in the valence band. But we should not or we need not take mass of electron and hole are both are same. So we have to take consideration wherein the mass of both the particles will be different. So we should know how to what is m then? M is basically the effective mass. That's important thing. Effective mass of exciton. What is effective mass? 1 by effective mass equal to 1 by me. M is mass, rest mass of electron, 1 by mh, rest mass of hole. So one mass, effective mass we have to put. We have a system, electron hole pair system. Now that system mass, effective mass we have to put in terms of AM in A0. So now effective mass means 1 by M effective equal to 1 by MB plus 1 by MH. Then now we should not say A0. We have to talk about exciton. exciton Bohr exciton. We are utilizing exciton Bohr radius AB equal to 4 pi epsilon 0 h class square by m effective q square. Understand now? So now we are coming to real world situation wherein we created an exciton in the semiconductor by absorbing some of the what's called optical energy. So optical, because of that absorption, electron from valence band goes into the conduction band. So in conduction band electron, valence band hole. So electron hole pair. So what is the distance between these two, electron and hole, exciton electron and hole? What is the distance? That is the exciton Bohr radius. So that is 4 pi epsilon 0. Why epsilon 0? Epsilon, because we are considering the semiconductor. So semiconductor dielectric constant is epsilon. Epsilon 0 is a dielectric permittivity of medium, which is a vacuum, and you know h cross square. Instead of m, we are putting m effective. What is m effective? Since we are considering electron hole, two particle system, we have to take 1 by m effective is equal to 1 by mb plus 1 by mh. So AB equal to 4 pi epsilon 0 h cross square by m effective q square. What is AB now? Distance between the electron and hole that is being formed because of the absorption of the light by the in the semiconductor. Okay, now we stop here. We talk it later because now already it is 5:15, more than that. So I would like to stop. So now you tell me if you have any questions. Please, you tell me if you have any questions. One fellow left already. 25, 23, 4 people are there. Now 24 people are there, including myself. Now, if you have any questions, please let me know. I'll be taking attendance. Please be there. Okay, it is already almost closer to 5:20, so I would like to stop here. So if you have any doubts, please let me know. Otherwise, you can log off. If you have any doubts, please let me know. Otherwise, you can log off.
No doubt, sir.
Okay, thank you. Please log off.
Thank you, sir.
Okay, fine. Okay, if you don't have any questions, please you can log off. Okay, I'm leaving.